Welcome to This Explainer. It's so easy to take for granted the literal millions of operations happening right under our keyboards every single second. But today, we're pulling back the curtain. We're going to see exactly how computers turn abstract math into physical hardware using just ones and zeros, and how software logic is translated into the physical silicon architecture that powers our entire modern world. Let's dive in.
Here is our roadmap for This Explainer. We'll start with representing numbers in hardware, move into fixed-point math for neural networks, lay down the absolute rules of binary math, look at building hardware calculators, and wrap it all up by coding and testing those circuits.
All right, kicking things off with Section 1, representing numbers in hardware, the ones and zeros.
So our very first problem is actually surprisingly simple, but it is fundamentally restrictive. How do we store numbers when we only have a finite amount of physical space, our bits, to represent them? Think about it. Unlike abstract math on a giant, endless chalkboard, hardware has strict physical borders. In silicon, the traditional infinite number line literally becomes a circle. If you have exactly 4 bits of physical space, you can only represent unsigned integers from 0 up to 15. And if you try to add 1 to 15, you don't get 16. There's literally no space for it. You run out of room, overflow, and snap right back around to 0, traversing that circle clockwise. It behaves exactly like a clock resetting at midnight.
Now, that circle concept actually gives us a really brilliant solution for handling negative numbers, which is a system called 2's complement. Because obviously, we can't physically build a minus sign out of silicon. So instead, we just shift our circle's values. By allocating the very first bit, the most significant bit, to act purely as a sign indicator, we split the circle. Half represents positive numbers, and the other half wraps backwards into negatives. So in our 4-bit system, instead of going from 0 to 15, our range seamlessly shifts to span from -8 all the way up to +7.
Moving right along to Section 2, fixed point for neural networks and how we handle fractions. Okay, so we've got positive and negative integers completely figured out. But now we face a totally modern hardware problem. Complex systems, especially AI and neural networks, absolutely rely on fractions for their weights and calculations. Traditionally, computers use these incredibly complex floating-point processors for fractions, but they are expensive and, man, are they power-hungry. That is not great for efficiency. So what's the workaround? Well, we can actually trick standard integer hardware into calculating fractions. We do this by simply pretending a decimal point exists at a fixed, static location within our standard ones and zeros. The hardware itself, it still just sees and processes a regular binary integer. But in our minds and in our system design, we are carefully keeping track of an implicit power of 2. We just mentally move that implicit point around when we add or multiply. It's incredibly clever.
But of course, there's a catch. Converting these highly precise fixed-point numbers to fit back into smaller hardware spaces presents a massive challenge. Say a calculation results in a fraction, like 3.5, but you need to turn it into an integer. If you always just truncate and round down to 3, or always default to rounding up to 4, you are going to cause massive, system-breaking error accumulation over thousands of AI calculations. We solve this with a really neat technique called banker's rounding or round to nearest even. The rule is simple. If you hit exactly halfway, exactly 0.5, you look at the whole number. 1.5 rounds to 2, and 2.5 also rounds to 2. This completely balances the statistical errors out over time.
And the best part is we can build this banker's rounding into a strict, step-by-step algorithm, effectively turning a complex mathematical compromise into a crystal-clear recipe for the hardware to follow. The circuit literally calculates the shift's difference, finds the quotient and remainder using arithmetic shifts, and then logically compares that remainder to the halfway point. It's just a beautiful example of translating a high-level statistical trick into the most basic hardware operations imaginable.
Section 3, the rules of binary math, dealing with growth in science. As we perform arithmetic with all these representations, we hit a very hard physical reality of digital design. Math literally causes the number of bits to grow. It makes complete sense if you think about it. If you multiply a 4-bit number by a 3-bit number, the result demands exactly 7 bits of physical hardware space to avoid overflowing our circle. It's an undeniable rule of silicon real estate. Every single time you multiply x bits by y bits, your resulting wire has to be exactly x plus y bits wide to guarantee you capture the largest possible result.
And when we're dealing with signed numbers, our multiplication solution requires 2 very specific steps to work. First, we have to sign extend the operands to that new, larger width. That just means we pad the front of the number with its sign bit to preserve its negative or positive value.
Then, as we multiply row by row, we have to carefully subtract the final row corresponding to the negative sign bit. Without that absolutely crucial subtraction step, the hardware would incorrectly process the negative values and give us complete garbage data.
Moving on to Section 4, building hardware calculators with logic gates.
Okay, now that we have all our mathematical rules thoroughly mapped out, let's actually build the calculator. We start with a basic truth table for a half adder. This solves the most foundational problem possible, adding two single-bit numbers together. If you add a 1 and a 1, the sum is 0, and you generate a carryout of 1. It's a super simple table, but make no mistake, this is the absolute bedrock of all computer processors.
This right here represents the actual magic leap from abstract math to physical silicon. We take that exact truth table we just discussed and implement it using real logic gates. We use a single XOR gate to calculate our sum and a single AND gate to calculate our carryout. Literally, by wiring these two physical electronic components together, we have successfully taught electricity how to do basic addition. How cool is that?
But obviously, nobody just wants to add two single-bit numbers together. To add large, useful numbers, we just chain these adders together. We take the carryout wire from the very first stage and plug it directly into the carry-in port of the next stage, creating what's known as a ripple carry-adder. The calculation physically ripples down the chain of silicon gates from the least significant bit all the way to the end, generating our final complete sum.
Finally, Section 5, coding and testing circuits using SystemVerilog.
While drawing gates is a great way to learn the basics, we definitely don't sit around soldering billions of gates by hand anymore. Modern processors solve this massive scale problem by using code to describe the hardware, typically using a hardware description language called SystemVerilog. But when we format our instructions for the compiler, we have to be incredibly precise about the size and format of our data. We use specific literals, like an 8-tick B for binary or an 8-tick H for hex, to define exactly how many bits wide our numbers are and what radix base they are using. This ensures our virtual wires are exactly the right size before they ever get etched into physical silicon.
All of this intense precision builds into what we call a full test bench. A test bench is basically just a piece of software designed to brutally stress test our hardware code. We define a timescale, instantiate our adder module, and then write code to rapidly drive random numbers into the input pins, complete with simulated time delays. Crucially, we write assertions, which are automatic checks that instantly flag an error if the physical hardware simulation ever dares to disagree with our expected mathematical logic.
When we run those simulations, we get to see the actual digital heartbeat of our coded circuit. These waveforms perfectly prove that as we pump random constraints into the input pins, our simulated hardware is calculating the correct sum and carryout over time. It's the ultimate validation. We get to watch our mathematical logic successfully map onto simulated physical wires, performing exactly as we designed it to.
Understanding how numbers flow through logic gates opens up truly endless possibilities for digital innovation. You've seen how we trick hardware with fixed points and how we mitigate errors with bankers rounding. So considering the strict physical bit width limitations we discussed in this explainer today, how would you architect a flawlessly accurate system? It's a massive challenge, and it's exactly the kind of problem hardware engineers solve every single day. Thanks for joining me on this explainer, and keep questioning how your digital world is built.